talk. What I'm going to talk about is mainly moist convection, because that's what happens in the atmosphere. We've got dry convection, but but most of the stuff which happens in the atmosphere is moist convection, because you've got, as air particles rise, they condense, they undergo phase changes, and you get water droplets, and then so on and so forth, and you get precipitation. So my main focus is basically to touch upon aspects of moist convection in reality and also in the model world. Oops. We've gone through some of these reasons why we study convection and why it's important for climate. Daniel highlighted that gravity waves, they also actually transport momentum. So tropical convection is actually helping to transport horizontal momentum upwards, and that actually affects stratospheric dynamics, which in turn affects surface climate, believe me not. It also drives global circulation by vertical transport and sensible heating. It's intricately linked to all the large-scale phenomena that you're familiar with, the Madden-Julian oscillation, Hadley and Walker circulation. So it's a key component of ENSO as well. So you've got where the SST anomalies are, your region of convection will tend to follow. Okay? And of course, with all the precipitation, we've got the essential part. It's a tropical convection is an essential part of the hydrological cycle. What I mean by convection driving circulation is you have different heating peaks due to the convective and the stratiform components. You have a higher peak due to the stratiform component, which is up in the mid-troposphere, up around 8 kilometers, and you've got a drying there as well due to the stratiform. This is in the lower part of the stratosphere, whereas if you look at the convective region, it heats up the entire depth of the troposphere. In the tropics, here we've got a plot from Schumacher and others. Basically, in the tropics, the stratiform fraction is about 40% in the mean, and they basically give you a horizontal circulation anomaly response, which drives the circulation aloft at around 250 hectopascals. So you have this heating in the tropics that basically generates a wave response that Steve was talking about, and you get this cyclonic, anticyclonic gyres, which is due to the electrical divergence and vorticity generation that drives circulation throughout the globe. And that's why tropical convection is important. There's actually a whole spectrum of convective clouds. You've got your shallow clouds, your congested or mid-level clouds, and your deep convective systems. And Daniel has talked about a lot about how shallow convection is important for climate as well. With deep convection, what we have to remember is that there's a deep convection, there's also the stratiform anvil part, and there's different processes which are occurring in the stratiform anvil. So there's different dynamics, they're maintained differently, and there's also different microphysics going on in the anvil region as compared to the convective region. In the tropics, a lot of the precipitation accounts for most of the rainfall. Here's a plot I got from Google by searching through the internet. You can see that these three cloud types can coexist within the same region. The horizontal scales are shown as such. So you have congestus, medium convection. One hypothesis is that they help to precondition the environment when they entrain moisture, which then facilitates deep convection. But then Daniel has raised the argument, or the debate that's going on at the moment, that it's actually large-scale moisture forcing which causes deep convection to occur pretty rapidly. But this is just a plot to show you that you've got three different types of cumulus clouds that can coexist at the same time. Now, the structures of deep convection can differ, or do differ, between land and over ocean. This is from a paper from Liu and others who looked at trim data. They looked at the brightness temperatures, and they define cold cloud features, or basically deep convection, with brightness temperatures less than 210 Kelvin. So these are really cold clouds that reach high up into the upper troposphere. And they basically show that, this is a schematic, and they basically show that the land systems are quite different to the oceanic systems. You can see there the cloud outline. You get fatter systems over the oceans. However, the updraft speeds in the land systems are much stronger and reach higher up. These are 40 dBz reflectivity contour lines. They reach higher up over land than they do over the ocean. And the 20 dBz line as well, which is the dashed line there. So they've got different characteristics that we have to take into account. And this is despite that their model, the modal, the middle level of neutral buoyancy being relatively similar. You have the modal values over land are about 14.2 kilometers in the tropics, whereas in the ocean, tropical oceans, it's 14.4. So there's not much difference. But you can notice that the spread in the LNB heights over land varies a great deal as compared to the ocean, where you have a more narrowed and peak distribution there. There's been studies by some modeling studies, some cloud resolving and some using aquaplanet simulations, which show a very strong relationship between tropical convection and water vapor. Large-scale organized convection in the tropics in their aquaplanet simulations require high levels of mid-tropospheric humidity. And then some other, the study by Derbyshire and others using the unified model at cloud resolving simulation show that deep convection tends to occur when there's high relative humidity over a large depth of the troposphere. Our own Steve Sherwood, way back in 1999, showed that CAPE is actually is a necessary but not a sufficient condition for the onset of deep convection. And what I mean by that is, this is the plot from his paper at the time, and he showed that you've got variable CAPE, but it's actually the humidity, high humidity above 70%, and you get this convection occurring. So although you've got CAPE in the atmosphere, deep convection takes time to occur. And it takes time. It only happens when there's large relative humidity in the atmosphere. This is the plot from Derbyshire, showing you they ran the model looking at the sensitivity of convection to tropospheric humidity, and these are their specifications: 90%, 70%, 50%, 25%. At 25%, all you get is just basically shallow convection over here, and they ran the model in cloud resolving simulation mode. So you've got sub-kilometer grid spacings, and you see the onset of deep convection basically starts to occur. It's when they prescribe a 50% or greater relative humidity value. So these are basically cloudy updraft mass fluxes. So you get a larger amount of mass flux over a higher depth when there's large relative humidity. And they compared that to another model, a different model, and ran at a 500 meter resolution, and the results are qualitatively similar. You get a higher depth of convection when you have high relative humidity over a large troposphere. This is another model that shows some behavior of convection that tends to self-aggregate in moist patches or moist regions. They ran simulations over large domains, and they found that over a certain size of the domain, convection tends to self-aggregate or conglomerate into moist regions. They found some sensitivity to resolution, but they do offer a reason why deep convection tends to self-aggregate in moist regions. And And that's basically because you've got different mechanisms for onset and then the maintenance of deep convection once that occurs. So they say the onset of self-aggregation is due to long-wave cooling at the top of low-level clouds in the dry region. And then once they come together, the state is maintained by clear sky cooling in the dry regions. And what this does is that this low-level radiative cooling creates a secondary circulation which is responsible for the upgradient transport of moist static energy. So you get a net export of moist static energy away from the dry regions to the moist regions, and that helps to maintain the self-aggregation of convection once it begins, essentially. They've got a nice video of this on YouTube, so you can actually look it up under, if you type in self-aggregation and Muller, they've got this simulation up on YouTube, which you can actually see the self-aggregation process happening. This is a conceptual model of a tropical squall line from Zipser in 1977. I just put this plot up there just to show you or give you an appreciation that there are lots of multi-scale processes occurring in deep convection. You've got your new towers, there are strong updrafts, your newest cells occurring which reach high up into the troposphere. You have, once they decay, they fall back into the stratiform region there. And so you've got this, I showed you your earlier plot, you've got deep convective and you've got stratiform region. And they basically form, the idea was that they basically form from these collapsing or decaying towers basically into the stratiform region.
The numbers?
The numbers are actually theta E values, equivalent potential temperature. So you've got basically in the tropics, you've got in the mid-troposphere, you have low theta E values, you've got high theta E values near the surface, and higher theta E values as you're up to the troposphere, There's a lot of processes going on there. You've got your front to rear mesoscale flows, your front to rear ascent, rear to front descent, and then you've got your entrainment at the cloud edges. So you've entrained these dry air during as the system convects. You have microphysical processes going on. This is related to cloud formation and precipitation formation. All these processes such as condensation, nucleation, collision, coalescence, a lot of these deposition, aggregation, rime, all these processes occur mainly in the stratiform region as well as in the convective region as well. And then you've got dissipation of cloud via evaporation or sublimation of the ice particles. There's a lot going on when you deal with deep convection, and that makes deep convection a complex problem to model because, as you know, each cloud is different. You've got different shapes, different sizes, different lifetimes, and also different forcings between land and the ocean. All these gives you uncertainties when you want to parameterize deep convection, and it is highly likely that the grid spacing needed to resolve all these individual convective elements range between 25 meters and up to 1 kilometer. So it is a complex problem, very complicated. We basically have two types of convection in models. Basically, one's parameterized. Steve has touched on a bit on that. And the other one's explicit, which I'll show you a bit later on. So what's parameterization? We basically want to represent the statistical or the bulk effect of all these subgrid convective and cloud processes in terms of the variables which we can predict in terms, so the grid scale variables predicted by the model. One of the most famous mass schemes, parameterization schemes, is the Arakawa-Schubert scheme. It's basically a mass flux scheme, so they calculate how much mass goes between one layer and the next, shown by that schematic over there. And the change in mass between each layer is basically a function of entrainment minus, so mass that's going in, and detrainment, which is mass that's going out over there. So we haven't really progressed much in terms of parameterization deep convection. A lot of the modern implementations of the mass flux schemes pioneered by AS74 have three components. You've got your trigger function. So this basically tells you when deep convection is activated, depending on whether the atmospheric state can support deep convection. You have your cloud model, which calculates the vertical distribution of heating, drying and cooling. And then you've got closure assumptions to close everything together. And a lot of the closure assumptions now relate to the relaxation of CAPE. So there's CAPE being produced by the atmosphere. This cloud-based mass flux is tied to the consumption of CAPE. So that's how they close the model. So, for example, the Canyon-Frisch convection scheme basically has a relaxation time step to reduce CAPE systematically as you increase mass flux at base. So these are basically your three components. I won't go into the details because we don't have time for that. So this is the plot which I'm showing you, the decision trees that each convection scheme has. So this is the one that I'm showing you for. Yep.
So the convective time scale that you're parameterizing these processes on, is that significantly smaller than the time scale of the gravity waves or the Rowntree waves or whatever else you're resolving explicitly?
No, it's actually I think it's actually larger. You have your gravity waves and your acoustic waves, the sound waves. They require a much shorter time step. Just to give you an idea of the time scale to reduce the CAPE in some of these convection schemes, they use an order of about 30 minutes or so to relax the CAPE back to equilibrium. So convection, the fundamental idea of convection is to drive the atmosphere back to a moist adiabatic state. So the free troposphere is in a moist adiabatic state most of the time. So the idea, if you have CAPE, the idea of convection is to drive it back to moist neutrality, basically. Yeah, so getting back to this, to decide when convection is occurring, they go through all these decisions, conditional statements to see whether the convection scheme should be called. The unified model actually treats both shallow and deep convection. So in the red, it's basically when the deep convection can be called, and in the orange is when shallow convection is called. The parameterization for the shallow convection is called in the unified model. So the unified model is the basis for our access model that we're using now. So this is the decision tree that the convection scheme uses. Steve showed you or mentioned that global models which use parameterization suffer from poorly representing precipitation, and he mentioned that they tend to rain too frequently compared to the observations. So his paper by Stevens and others, they used cloud set data, so it's part of the A-Train group of satellites, and the reason for that is that the models are raining too lightly at a given time step. So they just rain too frequently, but they rain too lightly. So you have some of these models at your typical GCM resolutions. You can show that compared to cloud set observations, which have been scaled up to match. So basically you're comparing apples to apples. Show that the models are raining too lightly compared to the observations, except for probably here you've got one exception, the NICAM in the tropics. The NICAM is a Japanese model, which Steve mentioned as a global, they claim it to be as a global cloud resolving model, but they still run it at 7 and 14 kilometers, so it's basically just resolving mesoscale circulations rather than being truly a global cloud resolving model. They found that their model is producing too much precipitation compared to the scaled observations. The models don't do the Dyson cycle of rainfall very well. The black line is the observations by trim. And you see the spread in the models there basically tell you the Dyson cycle over land and over the ocean is poor. You have errors in the phase and also the amplitude of the rainfall. They also don't do stratiform precipitation well. You've got observations on the left here by trim, and you've got all the different general circulation models. Oops. So you can see quite a spread in terms of the response compared to stratiform precipitation in terms of compared to trim. And the reason for this, that a lot of offered by Mitch Moncrief, is that GCMs don't resolve mesoscale convective organization really well. So they don't resolve circulations on the order of tens of kilometers, basically. So they don't. We're slowly beginning to understand the impact of emitting these mesoscale circulations, and recent parameterizations of convection have included these mesoscale updrafts and downdrafts, and has been recently implemented into the GFL model. So we are trying to understand and incorporate these effects into convective, these cumulus schemes. The other one is convection is done explicitly, where all the details of cloud processes are explicitly simulated. It's usually basically assumed that they resolve features of convection directly. Or do they? I mean, terms you find in the literature, you'll find convection permitting, cloud system resolving, cloud resolving, large eddy simulations, which can throw you off. So what I've done there is I've basically put the typical resolutions associated with these terms when you see them in the literature over there. So you would think that the cloud resolving model and the large eddy simulations would resolve all these cloud processes. The red bits are your common, your typical CRM grids, and you've got a few grid points there which cover even shallow convection. So it's sort of like the basic idea of an explicit representation of models. Just to show you differences between models, what I'm showing is the top of the atmosphere outgoing long wave radiation, so basically looking at OLR. And you've got unified model at 4 kilometers, WRF running at 4 kilometers. Basically, the unified model shows convection appearing to be too intense. Got these large blobs, cold, really cold temperatures. I've just basically color-coded them to highlight these cold cloud top features. And you've got these large blobs appearing compared to WRF, which seems to do a much more reasonable job. But are they realistic? At 4 kilometers, these are just convection permitting. They're not actually resolving a lot of the convective elements. A recent paper by Kane and others, when they looked at a 1.25 kilometer WRF simulation during TWP-ICE, showed that they can't, they don't model the timing, location, and intensity of the convective systems, even at 1.25 kilometers. And you have errors in the accumulated precipitation and rain rate. They redid the experiment with a much higher resolution, so basically a third of the resolution of 1.25, and then they compared the vertical velocities at 10 kilometers and then at 5 kilometers, and basically the updrafts remain too strong aloft at the 1.25 kilometer resolution, and it's basically consistent with the idea that it's a lack of entrainment or a lack of you're not diluting the updrafts with environmental air enough such that they are still producing these too strong updrafts appearing at higher altitudes. This is an image from one of our chief investigators, Todd Lane, who showed you the difference in the texture and the horizontal extent of deep convection when you model it with basically an order of magnitude less. You can see a quite different, size of these elements. The granularity of the anvil structure is different. can see that the horizontal extent of the stratiform anvil is much larger in the 1 kilometer resolution as compared to the 125 meter simulation. The updrafts are still too strong and still too fat and too wide. And they overshoot a lot more into the lower stratosphere. The more extensive anvil shows you that's too much water being transported. So there's more extensive diabatic heating, and this has implications for the radiation budget. So all this is consistent with lack of entrainment at the coarser resolution. Now, the concern has always been with horizontal resolution, decreasing horizontal resolution, but you can't forget about vertical resolution as well. Especially when you want to resolve gravity waves. You need to have a nice ratio between horizontal and vertical resolution as well. So as you can increase the horizontal resolution, you also need to increase the vertical resolution as well.
What is the typical vertical resolution
for these images? There are an order of about, well, for this one, I think the resolution, vertical resolution for that one was about 150 meters or so. And I can't remember what the horizontal, I would think they're on the order of 20 to 50 meters. Especially, Todd is more interested in how these, in gravity wave effects. And so when he does his cloud resolving simulations, he tends to have lots of vertical resolutions as well to resolve these entrainment processes and also these gravity waves. Just to summarize, we really need to get convection right because it's integral for weather forecasts and climate projections. The issue of increasing resolution will not give us a perfect GCM because there are always some scales that we don't resolve, like the turbulence and the microphysics. And if you just reduce the resolution, then the parameterization just becomes more microphysical. So you need to improve your microphysics as well, and that needs observational data, and there's been lots of recent field campaigns that focus on relationship between microphysical measurements or quantities of this ice, and they try to relate that to your deep convection that's been observed. So a lot of data there that can be used, that still has to be analyzed, so I'll leave it at that if there's any questions. Yep, okay.
Yeah, you showed some results from, I think it was Stevens, that presented some global cloud resolving frequency and intensity results, and there was some other models in there that look at different sorts. Is there any other studies that you're aware of that use an ensemble of these types of models to try and represent convective precipitation better?
Using
has that been tried?
Has that compared to satellite data?
Well, yeah, just to try and match up the conservation a bit better.
Yeah, there are. There has been some studies. I mean, not only compared to satellite data, but also field data that's obtained by these intense field campaigns like TWP-ICE and things like that. They've done some studies with GCM as well, compared to how they perform to the convective response to the Tropical Wampool International Cloud Experiment. But these are much smaller domains because they're much concentrated, a lot more concentrated over a small domain. Yeah, but there've been some studies, yeah, 1 or 2 papers which I've seen.
Yeah, and the results are okay?
No, they're still really bad. A lot of it has to do with the microphysics as well. There's a lot of variance due to the microphysics, how the models do their liquid water content, the ice water content, and things like that. So there's
so much resolution issue.
Yeah, my final point was that as you increase your resolution, the problem just becomes more microphysical. Okay. Yeah. Yes.
You had a comment about something Steve just showed us some slide. That means when people turn off the deep convections parameterized scheme, the rainfall come out better. You have any comment on that?
So the last?
Some last slide from the talk of Steve this morning.
Last slide from Stephen's talk?
Yes. And when we turn off the parameter
Yep.
the vapour from the water
Improves.
Wow. Yeah.
Did you show that?
The hurricane.
Oh, it's the hurricanes.
Yeah.
Yeah. As far as I'm aware, I think they play around with mixing length values and things like that. As far as someone from the Met Office, who I know, Stuart Webster, when he did some hurricane simulations, he switched off the convective parameterization, and he played around with the mixing length scales, and that seems to improve his simulation. So there's a lot of other things that go on when they switch off the cumulus scheme. Is try and mix, do something else, tune something else. So it's quite hard to make an inference. Yeah.